All right, our second presentation, Worry-Free Parsers with Parsley by Alan Short from Mozilla. This will also be a 25-minute talk plus 5 minutes at the end for questions. Please welcome Alan Short.
Hi. Welcome to Worry-Free Parsers with Parsley, as she just said, right. Every interesting program has to handle structured data of some kind or another, whether it's XML, JSON, CSV. We've got a nice little JSON object here with a Knight of the Round Table. And Python makes this really easy to parse. When you need to parse some data, we've got an HTML parser. We've got a JSON parser right in the standard library. So Python's great for this kind of thing. You're not always so lucky, though. Sometimes you have something like this that isn't JSON. It doesn't have quotes around the strings, or around the keys, and somehow sort of not appearing in this film got into the companions list. So you can't parse this with the JSON standard library parser. And maybe you have some ancient web API that expects the browser to eval the result, but you want to handle it in Python. So what do? You have to write a parser. Now, at this point, you have 3 choices. Number 1, you can do it wrong. And oddly, to me, this is the most popular option. As it's really tempting to just throw together some regexes and string manipulation and guesswork to write something that will extract something that you need. But as a famous post from on Stack Overflow by Andrew Clover reminds us, this doesn't always work out as well as we might hope. Some minor detail like white space might change, or we might have forgotten some case in the syntax that wasn't in our original example, or the 2 or 3 test cases we wrote, and the code breaks on later input. Trying to fix those complicates the code even more, making later breakages even harder to find, fix, and debug. Eventually, we spiral down into madness and despair. So we don't want to do that. What can we do instead? Another option is to manually write a recursive descent parser, where we manually iterate over each character in the string or token from a token stream, building a structure as we go. This works pretty well. This is how your C compiler's parser probably works. This is how the JSON parser in the standard library works. It gives you really precise control over your parser's behavior. But have any of you ever looked at the code in JSON? Okay, I see a couple hands here. How much did you love it? It's about 300 lines of code, and that's not counting comments or white space. And JSON's a pretty standard, simple format. I mean, the description fits on a business card. If you're going to parse anything more complicated than this, the code's going to be a lot longer. So for this and other reasons, parser generators were invented. And you could use that. It lets you write more code in less space by having a special syntax for it. And there are some good ones out there. There's Yak and Bison are the classic C ones. There's Ply, as Alex Gaynor showed in his talk on writing an interpreter. There's Antler, there's Spark, there's some others available for Python. But if you're in his talk, you heard him talk about how writing a parser is the most tedious and complicated part. Because if you think about, if any of you have used or looked at a parser generator, your first thought is probably, when I said parser generator, your first thought was probably about the same as mine, which is like this. And it works completely different from Python. You have like shift reduce errors, and you have like alternation between things and context-free grammars and DFAs and stuff and what. And so trying to debug that, trying to understand and write that type of stuff, always felt like I had to turn on a completely different section of my brain than writing Python. And so this is a real drag when you're trying to get new contributors into your project. Have you ever looked at PEP 306, which is the Python PEP for modifying the Python grammar, changing Python syntax? There's like 10 or 12 steps in there. You have to modify a grammar, then modify about 2 C files and about 2 Python files. It's not fun. So a lot of this came from a classic text on this, which was a book on compilers that describes the mathematical underpinnings behind parsing and the theory and so forth. And so this is good as so far as it goes. But most of the time, you're not writing a compiler. I mean, I love writing compilers. I think it's a whole lot of fun, but unless Alex Gaynor is here, maybe the rest of you don't. You need to parse something. You don't want to spend all year on it. What do? Fortunately, you need something that's readable and debuggable. Fortunately, there's been some new research on this in the last decade. We want something that lets us preserve our understanding of how to manipulate strings in Python, and your understanding of how Python code flows. But we want something with concise syntax, like regular expressions. People love regular expressions. I mean, that's how we got into that Stack Overflow post in the first place. So fortunately, there are now what's called parsing expression grammars, or PEGs. This was first described in 2004 by a researcher named Brian Ford. Unlike the previous generation of parser tools, they have a very similar model of execution to Python. So let's look at a regular expression here, a real simple one. This is going to match the letter A, either the letter B or C, then D one or more times, and then the letter E. If you've spent a few minutes with regular expressions, this is pretty easy to understand. The PEG expression for the same thing looks like this. We just put quotes around the literal characters. The slight difference here is that this compiles, or okay, I should say, when you read this, your understanding of this can be the same as reading this Python code. We're going to read a character from input, see if it matches A, and if that succeeds, we're going to match B, and if that succeeds, we're done. Or if it fails, we're going to try to match C, and then match one or more D, and then match E. So this is the expression part of parsing expression grammars. And so this returns a value. Since it uses and here, it's going to return the last thing, which is E. So the grammar part is you can give these rules names. So here we're going to give this rule a name foo. The reason that's interesting is because you can then call that rule by name. We're going to refactor our parser and move the B and C part out into a rule baz and then call it from foo. So this has the same effect as the example I just showed you, but we've separated out portions of it. You can also, since this is an expression, you can give names to parts of the expression. Here we're going to call baz. We're going to give the result the name x. And then we can modify the return value of foo by this arrow. And so we're going to return the value x. So this, if you call foo and it succeeds, it will return either B or C, depending on the input. So each operation in a PEG grammar corresponds to an operation in Python. And the mapping's pretty straightforward. We can call rules like we can call functions. We've got and or. We've got negation, fail if this does match. Then we've got star and plus and question mark, which work like they do in regular expressions. Match things 0 or more times, 1 or more times, or match it optionally. Now, there are some PEG-like things in Python. PyParsing and LEPL use there are parser combinator libraries where you string Python objects together using operator overloading and so forth to create a parser. Parsimonious, written by the incomparable Eric Rose, uses a very similar syntax to what I was just showing you. I chose to write my own library, Parsley, for a few reasons. One, I did want the brevity that this syntax gives of being able to express a pattern matching operation in as few characters while maintaining readability. The other thing I wanted was error reporting. A lot of these parser libraries, even the older and mature ones, don't give you a whole lot of error tracking information. If a parse fails, if you're lucky, it'll tell you what character it failed on or what line. If you're not lucky, it'll just say syntax error and you're done. And lastly, I wanted speed. By having this syntax, I could do some transformation on the back end to make things faster without having to change the user interface of the parser much. I still have a lot of ideas on how to make it even faster, but it's quite usable as it is. So let's go back to that JSON example. The JSON parser in Python is 300 lines of code. using Parsley, we can do this in 30. Here it is. I'll let you look at this for the next 10 minutes. If you have any questions, let me know at the end. No. But I'm showing you this. I don't expect you to read it. My point is just that it's not much bigger than this. So you can take what's written in an abstract description of the grammar and express it using this syntax. And a lot of times when you use a parser generator, you have to write some extra supporting Python code. This example didn't need any. If you need to do that in yours, you can do that with Parsley, but a lot of times you don't even need to. So let's dive into a couple rules here, just to show you what it looks like to use Parsley for something that isn't a programming language. We're going to show you a few rules out of the JSON parser. Just as a warm-up, here's matching white space. This looks about like it would in regular expressions. You match a string, a tab, carriage return, a new line, match it 0 or more times. So we're going to use this for skipping white space in between interesting characters in our JSON. So the object rule is the top level one. We're going to skip white space, match an open curly brace, then match some members. Skip some more white space, match a closed curly brace, and return a dict. And this is just Python's built-in dict we're calling here. And if you're familiar with it, you may know that this doesn't just take another dict. You can pass a list of key value pairs. So we're gonna create a list of key value pairs in the rule members here that we call. So members will call pair. And if that succeeds, it's going to give the result the name first. If it fails, then we're going to skip straight to the alternate here. We've got that or symbol. And it's going to return an empty list because we had no pairs. But if it does match, if we do match a pair, then we skip some white space, we try to match a comma and then another pair. And repeat that as many times as possible. And since this is an expression, star and plus will return a list of the things matched. So rest will be a list. So we then return a list of pairs. So let's look at the pair rule. We skip white space, match a string, match a colon, then match a JSON value and return a two-tuple. And so value is just going to be any JSON value, string, number, object, array, and then the constants true, false, or null. We would just return the right Python objects for those. I'm not going to show you string, number, and array. Array is almost exactly the same as object, just with square brackets. String and number are too large to fit on a slide. But, well, OK, I did fit them on a slide, but I'm not going to try to get you to read them. So this is how we use it from Python. We have JSON grammar with just all our rules as a string. We pass it to make grammar, and it returns a class. JSON parser is a parser class. Each rule that we described, like object, members, pair, string, etc., each is a method on that class. So the way we use it is this code example is in the Parsley distribution. We're going to just have a string containing some JSON here, create a JSON parser instance with that string, and call the object rule. And we get a dict. Now, this isn't interesting enough because we already have the JSON parser in the standard library. Let's look at handling that custom case we talked about earlier. If I pass in that not quite JSON string that doesn't have quotes around the keys and try to call the object rule on it, then we get a parse error. And this is the way the exception formats in your traceback. It shows you that it's a parse error. It points at the exact character where the parse failed. It's pointing at n, and it tells you it expected a quote there, or a closed curly brace, rather than something else. And trail at the bottom just indicate what rules it tries to call. So it's tried to call string, pair tried to call string, and it didn't succeed. So let's redefine those rules. Let's write a JS name rule that matches a JavaScript identifier. The angle brackets here mean collect what this matches into a string. So we're going to match a letter, and then letter or digit, and then $sign or underscore. This is basically the same as Python identifiers. So then our new pair rule will match either a JS name or string as the key, and then a regular value as before, and return that as a two-tuple. So we then call make grammar again, but this time we only wrote 2 rules. So we're going to say we're extending an existing parser. So this creates a new parser that overrides existing rules in the new one. So we can then take our not quite JSON text, create an instance of the parser with it, and call the object rule, and it works. So hopefully, this has helped you see how you can use parser expression grammars to take that next level beyond regular expressions for those harder parsing tasks you have. And I see I have 5 minutes, so I'm going to, OK. I have 10 minutes, OK. Sorry, I can't do math now. So I'm going to take a minute to talk about a little bit how Parsley works. So we have a rule like this. There is a Parsley grammar for parsing Parsley grammars. And don't think about it too hard. But that turns into a syntax tree, about like how Python would be parsed into a syntax tree. So we have names for these, ands and ors, and plus turns into many one down here. And so I have a compiler that turns this tree into Python code. And so this is a method in a parser class that does this parsing. I'm working on some other techniques that might compile into something else that's even faster than Python code. The PyPy guys probably have some awesome ideas for me on that. Plus, Parsley is not only useful for matching strings, so that's what I use it mostly for. You can use it to match any iterable. We have the bracket syntax here means match, read an iterable object from your input, and then match a pattern on its contents. So starting from the bottom here, we're going to match a string of digits and return that as an integer, or match a list or other iterable starting with star character and then two something else's. We'll talk about that in a second. And then match plus, or match a list containing plus and then two something else's, and do either multiplication or addition on them. So we can give it an input that looks like this. It's some nested lists. And it will iterate and recurs into that structure and produce an integer as a value. So you can write a parser that creates a tree and then write a tree parser that either creates a new tree or compiles it to something else. And so I haven't explored even the full potential of this idea, but I think there's a lot of interesting things that could be done with it. I'd be interested in hearing your ideas. Also, I should mention, I will be at the sprints. Come talk to me if you have a parsing problem that you want help with, or if you want to help make this more awesome. Thanks. Hi, Eric.
Hi, Alan. Great talk. I'm Eric Rose. I wrote Parsimonious, which is just about useful. Very similar to your library, but one of the things that you do is it's very conveniently, you put your tree transformers right next to your grammar. So here's my grammar, whatever. I can pull out this bit and make it a dict, for example.
Right.
What if, and just what if, I want to do a different set of tree transformers, but reuse your nice grammar? Is there any way that I can decouple those? Any thoughts on that?
I'm not sure what you mean by tree transformer. You mean like the arrow syntax?
Like you pull out, oh, I'm interested in this node. You pull out the number value, you didn't care about the parentheses, for example. Now, nobody wants the parentheses, but I could see cases where I might want some different nodes than the default wanted.
Yeah, I don't have anything for that right now. You have to explicitly indicate what you care about preserving in the input you match. So I haven't thought about that.
Cool, nice talk.
Hi, Alan. Nice talk. I, as you know, have some experience with the Python parser. I also tried implementing the Python grammar in various other parsers, and they're also always having trouble either with triple quoted strings or with the indentation as token. Does that work well in Parsley?
Corbin?
Hi.
Oh, you're in line. Okay, you moved. Stop that. The gentleman in the back there has written nearly all of a Python parser using Parsley. Sorry, I can't talk anymore. It handles the indentation of triple quotes fine. The part, I I think there's just some minor parts that haven't been finished yet, but in principle, it handles it just great.
Hey, very nice talk. I should be upset with you because I started a company called Parsley, parse.ly, but I'm not upset.
Well, that's why I spelled it like vegetable and not like the company. I saw that, I said, I can't do that.
Yeah, but,
I'll get in trouble.
But anyway, it looks like a really nice library. And what I'm wondering about is I see a lot of great libraries for doing like programming language parsing in Python. And what I'm wondering is there some sort of, some techniques from like compiler parsing that we can cross-apply to natural language processing? I
don't know much about natural language processing.
Okay.
Maybe so.
It seems to be the answer of everyone who writes a compiler parser, right?
So. Right, and my understanding is like the traditional LALR parsers came out of the natural language understanding of grammars and so forth, because they can express ambiguous grammars. Something like pegs can't express ambiguous grammars. They yield exactly one parse.
Okay,
so I'm not sure that there's much crossover there. If you want to come talk to me at the sprints, we can come up with something, I'm sure.
Okay, cool, thanks.
Hi, Alan.
Hi, Corbin.
So I'm not going to ask anything that I can't just ask you at sprints. Do you have the slide of Alex's grammar from a couple days ago?
I didn't get into a slide, but I did take about his 3 slides of parsing code and compress it into about 7 lines using Parsley.
Okay, that's all. Thank you for a great talk.
Thank you.
One more. Yes, great talk. Did you do any measurements as far as like performance against like PyParsing and those?
My experience with PyParsing is that I haven't done any benchmarks lately. An early version was, I want to say, 2 or 3 times faster, but I haven't. I've changed things around a lot since then. I believe it's even faster than that now, but
great.
Benchmarks are on my to-do list this week.
Thanks.
So I was wondering, if somebody were to contribute Python 3 support, would you accept that?
First, I would have to know if anybody was going to use it on Python 3, because I don't use it on Python 3, and I would not change. I would probably change something and break it on Python 3 and not notice.
Fair enough.
Thank you.